Today we're going to talk about Chapter 7-7, a few exponential functions that are going to be typical that you'll see in applications. Remember, with an exponential function, the variable is in the exponent. This is a times b to the power of x. These functions are not straight lines because the rate of change changes across the same graph. So we're going to look at this first example here. Y is equal to, here's just a general exponential function, a times b to the x, but we're going to have a specific function. We're going to let a equal 100 and b equals 0.5. Most of the examples that we'll do, this a value is going to be positive, and the b value is what's changing. If b is between 0 and 1, in this case it's 0.5, the graph will be decreasing. The graph will look like this. And if we wanted to take a look in our graphing calculator at 100 times 0.5 to the power of x, and if we want to change our window to like what we see here, you press window, and it looks like the x min is -4, the x max is 12, the y min is -10, and it goes up to y max of 100. And the scale on the y-axis, we're counting by tens. The scale on the x-axis, we're counting by 2. So if we took a look at this graph on our graphing calculator, it would match this graph with some specific points along the way. Every time x goes up by 1, y goes down by, it's 1/2 of its previous value. If you start out at 100, as x goes up to x equals 1, you're down to 50. When x goes up to 2, you're down to 25. Then you're down to 1/2 of 25, which is 12.5, 1/2 of 12.5. So you just keep going down, you keep decreasing by 1/2 because that's what this base tells you to do, is you just keep going down by taking 1/2 of the y value. If you want to take a look at the table of values, you start out with 100, 1/2 of 100 is 50, 1/2, 1/2, 1/2. So you just keep on cutting these numbers in half. This is called exponential decay because it's going down. In this other example, a is 1, the base is 2, b is greater than 1. Whenever b is greater than 1 and a is positive, it usually is, then this graph keeps going up. It's increasing or growing. In this example, every time that x is increased by 1, the y value doubles. So we start out with 1, then 2, then 4, 8, 16, 32, and you just keep doubling, doubling, doubling y, because that's what this 2 means, is you're going to double the y values for every x going up. This is called exponential growth. We use exponential functions a lot in the real world because we can model things that grow or decay as time passes, like populations, increase or decrease exponentially usually, bacteria, virus, the AIDS virus, radioactive substances. If you look at half-life, that's an exponential decay. Electricity, temperatures, and credit payments. That's just a few things that can be modeled by exponential growth or decay. Anything that increases or decreases by a fixed percent at regular intervals is either exponential growth going up or exponential decay coming down. We're going to look at some specific examples over here. We're going to look at a couple of functions to indicate growth or decay in applications. Right here, this is telling us that exponential growth occurs when this value is greater than 1. This is the base. B is going to be greater than 1. 1 plus r is equal to b for the base. And this one tells us that b, the base, is going to be less than 1. So like we saw on the previous page, this is going down. When you're talking about some specific applications, this a value is the initial amount. The r value is the rate of growth or decay. Usually you'll get it as a percent, and you need to change that to a decimal. And x is the number of time intervals that has passed, like years, sometimes minutes, or hours. Usually it's in terms of some specific amount of time. And the most popular application of exponential growth is when you put money in the bank. So this is money in the bank. If you want to know how much you're going to have in the bank, it's called the bank account balance, which is called A. If you want to know how much you're going to have in the bank, if you started off with P dollars, like if you have $100 and want to put it in the bank, P would be equal to 100. Banks usually give you some kind of interest, an annual interest rate, R. And you want to find out how much you're going to have after T. T stands for time, T years. If you want to figure out how much you're going to have at any time, this A is equal to the P, the initial amount you put in the bank, times 1 plus the interest rate, raised up to the T however many years after you put in the initial amount. So here's a formula that we're going to be using to find out how much money we're going to have in the bank if we started with $100. The bank is awarding us 4% interest rate, and after 12 years, how much money are we going to have? So we're going to start out with A equals P times 1 plus R to the T power. 12 years is the amount of time, so T is equal to 12. 4% is the interest rate, so the R interest rate, 4% is equal to 0.04. You have to convert a percent into decimal. And if you started off with $100, that's the P value. So P is equal to 100. How much money are we going to have? We're going to have 100 times 1 plus 0.04 to the power of 12. That much money after 12 years. So we're going to grab our calculator. 100 times 1 plus 0.04 raised up to the 12th power. We're going to have $160.10 after 12 years. Usually you round it to the nearest cent. And that's all there is to it. If you want to know how much money you'll have after 15 years, you're going to change T to 15. If you wanted to invest $1,000, you change P to 1,000, and you can figure it out that way. Or if you want to change the interest rate from 4% to 3%, for example, all of these things can change, and you'll find out how much money you have after a certain amount of time. Another very popular application of exponential growth or decay is population. In 1983, when I first moved to Kingston, the population was about 35,000 people, and the rate of growth was approximately 2%, 2.4%. Well, this is the rate of growth. R is equal to 2.4%, but you have to change that into a decimal. So if you move that back 2 decimal places, 0.024 is the growth rate, 0.024. All it is the decimal, or the percent changed into a decimal. We're going to write an equation to model the future growth, which means we're going to find out how many people were in Kingston in the years beyond 1983. So Y is the population at any time, and X is going to be the number of years since 1983, because that's when this whole example started in 1983. So the equation will be, instead of Y equals, this is exponential growth, A times 1 plus R to the X. Well, A is the initial population. A is equal to 35,000 people initially when this story began. So that's our A value, 35,000 people, because remember, A is the initial amount before things started to grow. And then you're going to multiply that by 1 plus, because this is growth. The growth rate is 0.024, and we're going to raise it up to the X power, which is the number of years since 1983. So there's our formula. And if we want to know what the population is in 1991, all we have to do is figure out how many years beyond 1983 1991 is. So X is equal to 1991 minus 1983, which is 9 years beyond 1983. And the population of Kingston will be 35,000 times 1 plus 0.024 raised up. I'm sorry, this should be 8 years. Raised up to the 8th power. So again, we can pull our calculator out and put that in our calculator. 35,000 people times 1 plus 0.024, the growth rate, raised up to the 8th power, 8 years beyond 1983. So the population of Kingston should be about 42,312 people. But now I want you to round it to the nearest 100. And when you round it to the nearest 100, you look at the tens position, which is a 1, and rounded, it's 42,300, rounded to the nearest 100 people. So there's our population with population growth. And the last page we're going to do for today is page 12. We're talking about depreciation now. We're talking about exponential decay. If you buy a new car, cars lose value, most cars anyways, lose value by a certain percentage each year. Well, Matt bought a new car for $25,000, but this car depreciates, or in other words, it goes down in value by 15% each year. Well, 15% is the decay rate, which is 0.15. That's the decay rate. We're going to write an equation to model the decay value. So y equals the initial cost of this car was $25,000, so that's the A value, $25,000. Because this is decay, it is 1 minus 0.15. This is R. And we're going to raise it up to the X power. X means the number of years since he bought it. So in 10 years, X is going to be equal to 10. How much will his car be worth? It'll be worth $25,000 times 1 minus 0.15 raised up to the 10th power. See how much this will be worth. $4,921.86. So in 10 years, it's lost that much value from $25,000 new to $4,921.86 after 10 years. And then the last example we'll do today is on batting average. This is for anybody who's interested in baseball. Jose went 2 for 5 in his first baseball game. His batting average decreased by 0.3% each game. Poor Jose. Well, his initial batting average, this is the A value. If Jose went 2 for 5, 2 for 5 is 2 over 5, and that turns into 0.4. So our A value is 0.4. What is the decay rate? Well, if he went down 0.3%, the R value is 0.003 because you have to move that decimal point over 2 spots. And now an equation to model his batting average after each game. Y is equal to the initial batting average, which is 0.4, or you could use 2 over 5 if you wanted to. And because it went down, it is 1 minus 0.003 raised up to the X power. And X is equal to the number of games he's played. Y is the batting average. So there is his batting average after each game. And at the end of the 161 game season, Jose will have a batting average of 0.4 times 1 minus 0.003 raised up to the 161 power because X is the number of games that he's played. So there's the formula for his batting average. Let's put that in. 0.4 times 1 minus 0.003 raised up to the 161st. That's after the last game of the season. Poor Jose, he ends the season with a 0.2465, which is 0.247 batting average. Usually batting averages are 3 decimal places. So that's it, and tomorrow we'll have some practice problems to do for exponential growth and decay.